So brace yourself up. I will switch what I plan to do for tomorrow today because I think it's friendlier for this hour. Feel free to stop me at any point for questions and or comments. And that's it, let's begin. So what I'm going to talk about is cutoff. The cutoff phenomenon. So the cutoff phenomenon is something that occurs in something from probability theory, and it was kind of discovered in the 80s and gained some popular attention under the idea of card shuffling. So did you ever hear that 7 shuffles are enough for a deck of cards? So it's about that. Percy Diaconis and I think, proved in the 80s that if you look at a deck of cards and you do the shuffling, and the shuffling is some random mixing of the cards, and they ask they look at how many times do you need to shuffle in order that the deck is well permuted. So there are many permutations, 52 factorial permutations. And you want your random shuffling to be closed in probability space to a completely random shuffling. And they looked at the distance. So that would be a distance from uniform distribution as the number of shuffling goes. So we call it T for time usually. And they noticed that it kind of look like that. It starts with no randomness at all, and it stays not really random until some point where it becomes very random, and that's it. And this was called the cutoff phenomenon. That all the mixing occurred at a specific point in time. So let me say it now formally. A sequence of graphs xn as the cutoff phenomenon if for any epsilon, any positive epsilon, the mixing time, the epsilon mixing time of the graph and the 1 minus epsilon mixing time of the graph are roughly the same. So we would say that as you go farther away in the sequence, or as your graph grow, the epsilon mixing time and 1 minus epsilon mixing time becomes the same. So think about, would you like your distribution to be 0.1 away from the uniform distribution, or 0.9 away, which is very far? This is pretty close. And Diaconis, it doesn't matter. You still need, for this or for this, you need 11 shuffles. In their case, it was 7, but they chose 7 only for publicity reasons. You look where 7 is, and it doesn't make sense at all. Nobody ever checked that. So is that definition clear?
No. What is the mixing time?
Oh, exactly. So I want to say, what is the mixing time? The mixing time of a graph is the minimum time such that the distance of, so now let's think about random walk-on graphs. So this is PT or PT V naught is a distribution of a random walk starting from a vertex V naught at time t. So this is the distribution on the vertices. You start from a vertex V naught. At every step you move to a randomly chosen vertex, uniformly at random, and after t steps you ask, okay, what is my distribution now? And I'm asking what is the distance from uniform distribution. Uniform distribution would be the 1 over number of vertices. And I want this to be at most epsilon. So The epsilon mixing time is the first time at which my distribution is epsilon away from the uniform distribution. I know that's that for any starting point. So
What distance do you take?
Hmm?
How do you measure distance?
Oh, and that's the next thing. We have to pick some measure of distance, but whatever your measure of distance, it makes sense now to talk about the cutoff with respect to that measure of distance. And so far I just wanted to see the flavor of the game. In reality, what we care about is the total variation distance, because that's the most, the one that tells you the most about distance between two probability measures, and it's defined like that. So you have two probability measures, let's say I and mu, and it's a bit hard. It's the how much can these probability measures disagree on an event. So this would be, well, let's say we talk about vertices in a, we're walking on vertices in a graph, so event is just a set of vertices, and I ask for any set of vertices, how much can these two measures disagree? Now this sounds a bit scary because you have to go over all subsets of the vertices, but here's the classic. Here's your first exercise. This is just 1/2 the L1 measure, so you know it. But it's nice sometimes to think about it like this, sometimes like this, and it's a nice exercise. So this is the distance we're going to use, and this is the distance function that interests people in probability theory. Questions? So let me show you how it happens. So here is why cutoff happens. So let's take a regular graph X, and A would be the adjacency matrix of this graph, and the spectrum of A, as we saw many times, is K is the 0 eigenvalue, then there is the second one, and then up to lambda n minus 1, where n is the number of vertices. And we're going to let's denote lambda to be the maximum of lambda I in absolute value from 1 to n minus 1. So the maximal size of an eigenvalue except for the trivial one. This is, as Shai said, also the Rayleigh quotients of functions orthogonal to the constant function. I would say I can think about it, the operator norm as the adjacency matrix, but restricted away from the constant function. So the constant function has eigenvalue k, and the other eigenvalues belong to the orthogonal complement.
So in the bipartite case, we want to exclude n minus 1?
Yeah, the bipartite case would be terrible here, because that would be k. Now I don't allow you. I allow you, but it will be bad. So let's look what happened when I start walking on the graph. So the basic observation is that the distribution at time t plus 1 is just the distribution at time t applied to A divided by k. Because you apply the adjacency matrix, you sum the probabilities of your neighbor, divide by k, that's the probability you'll get to that vertex. And therefore, the probability of time t is just A over k t, t naught and t naught, t0. And t0 is just the indicator function of your starting vertex. So let's do the exercise. What is the distance from the distribution of time t to the uniform distribution? The uniform is a constant distribution. We're interested in total variation, and we're going to do the following. So as we said, this is just a over k to the t delta v0 minus u. Now, a over k to the t, that's the evolution of the distribution during the walk. What does it do to the uniform distribution? Nothing, right? The uniform stays uniform, so I can add parentheses here. And after I add parentheses, this is orthogonal to the constants, because these are two probability distribution. But the point is, I'm still at total variation norm, so I can't yet use spectral consideration. So how do I use spectral consideration? I do the stupidest thing. I say, oh, this is L1 norm, and I learned from Wikipedia that L1 norm is bounded by the square root of the dimension times L2 norm. This is half the L1 norm, but forget, there is a half here, but I'll forget about it. It's not helpful in any way. I will take the k to the t out already, and I'm left with at of delta v naught minus u, 2 norm. And with 2 norm, I know how to work. So this is orthogonal to the constant function, and the operator norm on the orthogonal to the constant function is bounded by lambda. So I get here n, s square root n, k t, lambda t, and actually the norm, well, the norm of delta 0 minus u, but this is actually smaller than 1. That's okay, that's another exercise. Check that this is smaller than 1, so I get this, and I want this to be small. Now, here's the fascinating thing, why the cutoff occurs. Let's say lambda is bounded by square root of k. So this is a very good expander. The eigenvalues, except for the first one, are bounded by the square root of the degree. And what you get here, is n over kt squared. And when is this bounded by epsilon? So I did the exercise for you. It's log kn plus twice log k 1 over epsilon. So log kn to kill the n, and then log k 1 over epsilon to get from 1 to epsilon. And the 2 here is because of the square root. Okay, so this is the, at this time, I will be epsilon away from the uniform distribution. And see what happened here. I walked on a k regular graph, so, and I need to get to n vertices, so log kn means it makes sense. And then what happens here is the part that, okay, I only need to walk to get to epsilon doesn't depend on n. And let's see what happens on the other side. So on the other side, I'm measuring the probability, distance of probability from the uniform distribution. And now I want to think about the other way that I told you to think about total variation. It's the maximum of how much they disagree on a set. The set I'm going to take here is the complement of the t-sphere around the starting point. T-sphere around the starting point, I just mean all the ends of passes of length t beginning at v naught. Nothing special, and I don't care about backtracking, non-backtracking path, all paths. So what happened? This is at least how much they disagree here. So this is tt of a minus the uniform probability of A. But what is the probability to be on A at time t?
0.
0, because that's how I made it. So I'm left with the probability to be on A. What is the uniform probability to be on A? So it's the size of A over the number of vertices. The size of A is n minus the size of this figure. And because the graph is k regular and I walked t steps, this is at most k to the t. At most. So what I'm left with is that this is at most 1 minus k to the t over n. But if I want this to be at least 1 minus epsilon, what do I need here? Almost the same thing. I need t to be log kn minus log k 1 over epsilon. So now if you draw our graph, you see here log k n. Here is minus log 1 over epsilon. Here is twice log 1 over epsilon. And you see that in this window, you went from 1 minus epsilon to epsilon in your total variation distance. So maybe you're walking on a graph of size 1 billion, and of course for that you need log k billion steps. But now I'm telling you, yeah, but it doesn't matter if you went on billion vertices still to be 1.1 away from uniform. You only need something which depends on 0.1. It's very surprising. So how come we get it so easily?
The assumption on lambda.
What?
The assumption on lambda. Because of the assumption on lambda.
Yeah, this is really strong. Do you know such graphs? Yeah, you know. But like for example, we saw at least 2 in this course. So, for example, the complete graph. Come on, allow yourself to cheat. The complete graph satisfies this. Remember what is the second eigenvalue of the complete graph? It's -1. So yeah, it's bounded by square root of the degree. But also the Heawood graph has this, and as Shai Sfer, the analog of the Heawood graph over general fields, so lines and planes in FP cube, have this property. But the point is, as we said, the number of vertices grow for these graphs. So if along Bufana tell you that there is no infinite family with lambda bounded by the square root of k. So I remind you, it tells you that lambda has at least to go to twice square root of k minus 1. So how do we solve this problem? Okay, first of all, we did just prove the cutoff phenomenon for the sequence of Heawood graphs, for the sequence of projective planes. And that's fine and interesting, but we want to understand what happened with expanders, which are families with constant degrees or bounded degrees. And here is what I'm trying to get at, a result of Lubotzky-Phillips-Sarnak from 16. We said that Ramanujan graphs have cutoff. And I also want to say there is a conjecture due to Perez from around 20 years ago that expanders in general have cutoff. It's completely open. We have no idea how to approach it. And this was a major breakthrough. So in 2016, the proof that at least Ramanujan graphs at the best expanders have cutoff. So that's what I want to show you now. You ask how it relates to high dimension. So what I'm going to do now is take x to be k plus 1 regular. Okay, I went higher, and maybe it will help me. Yeah, very tired. Yes?
The difficulty is that when you take from a Ramanujan graph, the extra two factor doesn't allow you something that you have on top to work.
Say it a bit louder.
Well, for a Ramanujan graph, it is harder because this argument doesn't give the lower bound. Because
Well, what we just did doesn't work because we have this and we need this.
I see.
And this is, by the way, here I didn't use the spectrum at all. That's a nice point, right? I didn't use the spectrum. So this bound is true for any k regular graph. The spectrum was used only for the other side. So why am I taking x to be k plus 1 regular? It's still a graph. I didn't go to higher dimension because I'm going to look at the non-backtracking walk. Non-backtracking random walk. So I won't write it. It's non-backtracking random walk on edges. On, let's say, directed edges. I should stress my graph is not directed. It's an undirected graph, but I'm walking on directed edges. It means that if I'm on this edge, I'm walking to all the edges that leave this vertex. I'm walking to one of these. There is also an edge going back, but I'm not going to it. And there's edges coming here. I'm not going to it. I only follow the edges. So let's do it formally. Here is the operator B, which acts on functions on directed edges. So I write E plus or E directed. Yeah, match with itself. What does it do? If I have a function, so I'm trying to find the analog of the adjacency matrix for this walk. If I have a directed edge from V to W, I'm summing over all the vertices U, all the edges which lead from W to U, except V. And this operator controls the random walk, the non-backtracking walk on directed edges. If you ever thought about non-backtracking random walk as a process on vertices where you remember your previous vertex, don't. Think about edges. This edge tells you where you are and what was your previous vertex, but it's just nicer to think about edges. So now, we start with some edge, some directed edge, and we ask what is the distribution to, what is the distance to a uniform. This is 1 over the number of edges, and I'm going to call now the number of edges n. Okay, so the number of vertices, we're not using it anymore because we're walking on edges now. And I'm curious about that. And we're going to do, we can do again everything, but eventually we know what we care about is the second eigenvalue. So here is the remarkable thing. So this is Ihara, Bass, Hashimoto, and so on. A lot of people fail. A lot of people contributed to this wonderful identity, which tells us that the spectrum of B, the spectrum of the non-backtracking operator on edges, is the following. We take the eigenvalue of A. I should do that. We take the eigenvalue of A, and for each eigenvalue, you take lambda plus minus lambda square minus 4k over 2. Did you see this week? This thing, I think, somewhere in Alan's talk? Okay. Now this is not enough, right? There are less vertices than edges. So there are eigenvalues that I missed here, and it turns out they're all plus minus 1. So these are very simple, they don't interfere, everything else is larger, and we can really forget that these exist, they don't bother us. Here's the interesting part. And what happens, here's, okay. So you remember what is Ramanujan? When is the graph Ramanujan? What do you need for the spectrum of adjacency? Now come, somebody. Lambda should be bounded by? 2 square root of k. Why k? Because it's a k plus 1 regular graph. So, okay, what happened when lambda is smaller than 2 and twice square root of k? Lambda squared is smaller than 4k. So that's exactly like saying that the root is imaginary. And when the root is imaginary, the norm of this, let's call this guy mu. Mu would be mu, and we have two of them because of the plus minus, so let's call them mu and mu prime. So what is the absolute value of mu if this part is imaginary? So it's lambda squared minus this, lambda squared. So we have 4k square root over 2. It's exactly like saying that mu is exactly square root of k. And everything is vice versa. So Ramanujan for the eigenvalue is of A is the same as the eigenvalue of B of this side. This is Sunadas pointed out that if you're writing mu as e to pi theta k, no, sorry, as k to the s, then this would be saying that S is in half plus IR, which he called, oh, this is the Riemann hypothesis. But this is again marketing. Okay, so we got what we want, you remember? That's what we said we need for cutoff. So the degree of non-backtracking random walk is k. That's why I took here k plus 1. Maybe I should have stressed that. I take here k plus 1, so I'll have k for the degree as I'm used to. And I discovered that the second eigenvalue is the square root of k. So lambda is square root of k. Do I get cutoff? It seems fine, right? But I will help you. Well, the theorem I just erased, Ramanujan graphs have cutoff of Lubotzky-Phillips-Sarnak in 16 is even in GAFA. So it can't be that easy. Right? Ihava, Bas, Hashimoto, say that's an old result. So this the relation between the spectrum of adjacency and non-backtracking was understood way back. So this is not enough, otherwise, yeah, they won't get it in GAFA. So what's wrong with the argument we gave? Why doesn't it work for the non-backtracking random walk? You can guess.
Is it because the corresponding operator is not self-adjoint?
Yeah. B is not self-adjoint. Self-adjoint and not normal, and therefore the operator norm of B restricted to the orthogonal complement of the constant has nothing to do with its maximal eigenvalue. That's mu. Not the trivial one. Just because it's not normal. You know what controls the operator norm in general of non-normal matrices? It's not the eigenvalue, it's the singular values. You heard this? Who heard this term? Yes. That's the point. We have to take care of the singular values, not the eigenvalues. We want the singular values. The singular values are harder. Another interesting thing is, remember we want to take B to some large power. Another interesting thing is for non-normal matrices, this doesn't have to be the power of the matrix. This would hold for normal matrices, for self-adjoint matrices, but that's another thing that breaks down. So we have two things that break down because our operator is not normal, and somehow they will fix each other. So let me show you what happened. This is an idea, by the way, due to Kotani and Sunada. Very beautiful. We're going to find not only the eigenvalues of the non-backtracking operator, but also the eigenfunctions. So let's say we already found an eigenvalue, an eigenfunction of the adjacency operator with eigenvalue lambda. We're going to use it to construct eigenfunctions of the non-backtracking operator. So we're going to define the head of f and the tail of f. The head of f is the operator that to a directed edge gives the value of f on the head of the arrow, and the other one is the tail of the arrow. And let's see what happens when we apply the non-backtracking operator to this f. So let's say B head, and I'm evaluating this on some directed edge. So B tells me sum over all the u except v of f head w to u. What is f head of w to u? fu. And what I want to do is add back v, which was omitted. So I'm saying, okay, go ahead and sum over all neighbors of w, fu, but omit v, because we didn't have it. But what is this? I'm summing over all the neighbors. That's exactly the adjacency operator applied to f at w. So this is lambda fw minus fv, which is lambda f head minus f tail at the same edge I started with, at v to w. So this means this means that I'm going to take B, I'm going to restrict it to the span of the head and tail of the linear span of the head and tail function, and ask how does this operator looks on this two-dimensional space. So I'm taking this as a basis. Now you need to check they're independent. That's an exercise in the exercises I put online. What we just discovered is that this begins with lambda minus 1. If I take f head, B takes it to lambda f head minus f tail. Now, do you want to guess what will be the second column? Come on, take a guess. Good, you're careful. It's K0. You had no way of getting it. So this is an exercise. Finish. It's the same type of argument. It's just surprising because you expect it to be something similar. But no, this is not symmetric. The non-backtracking really goes in the head direction, not the tail direction. So finish this matrix. But this matrix, what are its eigenvalues? They're written on the board. And you could have known that because I told you that these are the eigenvalues of B. Here we just broke B to a little part. The little part came from lambda. And I'm showing you where the so first of all, we proved the Ihara-Bas-Hashimoto-Serre theorem. We found the eigenvalues of the non-backtracking matrix. This was the Kotani and Tsunada idea. This is what they wanted to do here. But we also found the eigenvectors. So the eigenvectors, if you find them, are going to be mu f head minus f tail and mu prime f head minus f tail. And you could be happy with that. But the point is, the operator is not normal. And when the operator is not normal, the eigenvectors are not orthogonal to each other. So what we're going to do is throw away this guy. We're going to stick with one eigenvector. And just because we have a two-dimensional space, we can complete it through an orthonormal basis by hand. We're going to find, so this is one eigenvector, and we're going to complete this to an orthonormal basis. So I'm going to take this guy, I'll call it F, and which is mu f hat minus f tail, and then you compute the what is the orthogonal complement, and this guy mu f hat plus minus f hat. And it turns out this is oh, I didn't give him a name. This will be f prime. It turns out that this is an orthonormal basis up to scaling. It means that these two vectors are orthogonal and they have the same norm. I didn't bother to normalize them because it will not affect our matrix. I should say, here for the first time I used the fact that mu should be square root of k, or lambda is in the Ramanujan, but I'm Ramanujan. If you're not in the Ramanujan regime, this is still a basis, but they're not orthogonal anymore. And how does the matrix look? In this, so this is B restricted to this space, the F head, F tail space, in my new basis. So the first guy was an eigen vector, so I get mu and 0. And the second guy is really beautiful. It turns out it's k minus 1 mu prime, but let's put here mu bar because we know from this that mu and mu prime are conjugates. This also implies that mu prime is mu conjugate, so I can forget about the mu prime. Now you remember, okay, that mu has, we know its size, and we can write mu, we're going to write mu as e to the I theta square root of k, because we know its size is square root of k, so we're just throwing the argument. What is lambda? It's mu plus mu bar, and this is from here.
Cos theta.
Mhm.
Cos theta.
Right, so I have square root k and cosinus or twice?
Twice.
Twice, right? Square root k cosinus theta. So this did appear in Alan's talk, but it was so many years ago that you have no recollection of ever seeing that. Remember, he did this picture with the theta going here, here, here. That is that theta. Same theta. And now we're going to look what happens when I take a large power of my b, because that is what everything about when we study random walk. We have this evolution operator, we take large power. The point is we already broke b to a lot of small pieces we understand separately. And if I, for each of these pieces, let's take this guy to the L power. So mu is square root of k. Sorry. And we get t. So I'm taking square root of t outside, and then I'm left with I theta, I minus theta, and here I have k minus 1 over the square root k that I took outside. That's it. To the
Square root
t.
of k?
Sorry?
Square root of k, not t, yes?
Square root of k. And the point is, that's a triangular matrix. We know how to take powers of them. So k to the t, and here it's e to the I t theta, e to the minus I t theta. And here, if you ever did this, you're left with what you had before. And then you add all the sums of power of this and power of this with sum to t. And you'll do the exercise and find out that if you do that, well, it's something exponential, together they should give you something trigonometric, and what you get here is sine t theta over sine theta. And this you should also remember from Alan's trace formula. So I will say that you can get from this to the trace formula without having to manipulate the black magic of generating functions, if you're willing to go to walk on edges and not on vertices. Because I still have phobia from Chebyshev polynomials, so whenever I see Chebyshev polynomials, I say, oh, okay, let's do it on the edges, and then everything becomes playing with 2 by 2 matrices, but you get eventually exactly the same thing. And we remember what we wanted was to bound the L2 norm, operator norm of the power. And as I said, this is a non-normal operator, so bounding the L2 norm of the original matrix B doesn't tell us about its powers. That's why we really computed the power. So what happens here from this guy? I get square root k to the t from here. And okay, now it's this is 1 in absolute value, this is 1 in absolute value. This thing, and that also, as I said, this is bounded in absolute value by t. The most that you can get here is t. You can also see it because you actually got it from adding t quantities of size 1. So you're left with 1 from here, and here is something like square root of k, and this is t. So, okay, do it all together. You get from this t plus 1 and t. And the t came from here. And the square root, and then there's another square root coming from here. And this, now we win. Now we won. You remember what we wanted? We wanted you have that the norm of b away from the constant to the t. We wanted it to be bounded by square root of k to the t. We wanted the square root of the degree to the side of the walk to get cutoff. What we got is really, really similar. This is the idea. So it's almost the same up to a logarithmic factor. This is logarithmic in what we want. And then it's left as an exercise to show that the epsilon mixing time from this, you can show that directly that the epsilon mixing time is log kn, so that's what you got to have. And then you remember we had log k1 over epsilon. Instead we're going to get log, actually 3 times log n. And this compensates for this guy. So that's just doing the computation, and it's a nice one. How much time do I have?
3 minutes.
3 minutes? Okay. So, right now you saw the Lubotzky-Phillips breakthrough.
Bobby, where's the epsilon here?
Sorry?
The epsilon here.
The epsilon is swallowed into the log n.
Ah.
So for any epsilon, you could add here, if you want to be really, really, okay, you could add this here, but this will swallow it pretty soon for large enough.
Yeah, I have a question. I hope it's not too stupid, but so you're saying that any function on directed edges can be written as a linear combination of heads and tails?
No, the idea is plus minus 1 at the end.
Okay, so that's also still...
And I'll tell you where they come from. They come
Okay.
from taking a cycle and putting 1 on these edges and minus 1 on these edges. And now if you apply b to this, then the 1 goes to the 1, the minus 1 goes to the 1, and any edge that goes outside get minus 1 and 1, so they cancel. So you got an eigenvalue with eigenvector with eigenvalue 1, and I leave it to you to find the minus 1. And also you know that the number of independent cycles is exactly what you're missing, the number of edges minus number of vertices. So everything else is filled by these guys. But because 1 is much smaller than square root of k, they don't bother you for the analysis. Okay, so I wanted to connect this to things that were said during the last few days. Anyway, I really love this proof. This is a proof of Lubotzky-Phillips result, and it's beautiful because it answers something that was open for like 2 decades with tools that belong to second course in linear algebra. I always love things like that. How does it connect to our world? What happened here, what saved us, was the fact that even though the matrix is not normal, it decomposed to blocks of size 2 by 2. Now what happened here behind the scene, behind the scene is, you remember that the Hecke algebra of the maximal compact and a group in, let's say, PGLN is commutative. So that's something that Animali said, and because it's commutative, it means that one-dimensional representations, that's irreducible, have dimension 1, because it's a commutative algebra. Now, this relates to graphs because this is the algebra of operators on the vertices of a tree or a building or a complex. But we're working on edges, and edges, as I think Shai said, operators, geometric operators on edges, by the dictionary Shai was trying to sell to you, correspond to Ivahori operators. So operators in the compactly supported function on which are by Ivahori stable on the group. And today Anna-Marie showed us really sophisticated things about this algebra and its representation theory. But one thing I think that is not trivial from what we showed is that this, the Ivahori Hecke algebra is quite commutative. So if you looked at we actually got relation. What happened with when we multiply two generators? Well, they don't commute, but they commute up to something which depends on the veil structure and so on. And eventually, okay, but this is in parentheses. What actually happened is that irreducible have dimension at most d factorial, where d is the dimension of your building. No, not the dimension of the building, it's the PGLD, is the dimension plus 1. PGLD. We're in graphs. Graphs correspond to quotient of PGL2. So we get d factorial, which is 2. So the irreducible representations of the Ivahori algebra have dimension 2. And these are the 2 by 2 blocks that we see here. So this tells us, and this is not how Sunada and Kotani thought about it, but coming to this from the perspective of a building, this is what happened, and this is how it will generate to higher dimensions. Okay.
Thank you.